Good morning. I think we can start. We just have some little technical problem, but it's all fixed now. So good morning, everyone. Thank you for coming to this California Air Resources Board Research Seminar Series. And today, the topic is a method to prioritize source for reducing high PM exposures in EJ communities in California. I'm Zoe Zhang, this research contract manager. And before we start, I just want to point out to those who join us online, you can go to our research seminar webpage to download today's slides. And also after today, we're going to upload today's video to the same webpage, so you can always revisit our talk today and discussion. And before I turn this over to our speaker, Dr. Josh Aptis, I want to give a brief introduction why we founded this research. What's the purpose of this research? So we all know exposure to high PM level can have been linked to a series adverse health impacts, including like heart and lung diseases and premature deaths. So many policies and programs has been implemented to reduce ambient PM to 2.5 levels in California. However, in the past decades, we have seen California's ambient PM 2.5 have been reduced by up to 30%. However, EJ community is still exposed to persistently high PM 2.5 levels than non-EJ community. So it's very important for us to identify sources that contribute to PM 2.5 exposure disparities, and also prioritization of emission control is also very important for us to achieve the goal to provide clean air to all Californians. However, sources of air pollutions vary dramatically in their impacts on population due to first the total amount of air pollutants emitted, and also by its proximity to populations. So for each unit of pollutions emitted, sources located in urban areas of high population densities may have higher impacts than those in rural areas, because pollutants emitted in those urban areas can more easily reach to people's breathing zone and impact more peoples. So that's why it's for protecting public health perspectives, it may be more efficient if we prioritize source control, not only by the quantity of air pollutants emitted, but also by its impact on exposures. So that's why California Air Resources Board founded this research, try to develop and use as screening tools to prioritize source reductions by its impact on exposure. So with that, today, the speaker is Dr. Josh Aptis. He is an assistant professor of environmental engineering at the University of Texas at Austin. And his research interests include methods for air pollution assessments at local and global scales, atmospheric aerosol dynamics, air quality, environmental justice, and environmental sustainability in low-income areas. And he holds a PhD in energy and resources from UC Berkeley, and has published over 40 articles in peer-reviewed journals. So with that, please join me in welcome Dr. Aptis.
Thank you all for being here and for showing up in person, for being online. For those of you who are online, I'm just going to switch slides here briefly. Showing up? Yes, great. There is basically a trade-off between you guys being able to see me and being able to see the screen. So I'm fine with me being in the dark. You guys came here for what I'm going to talk about, not to see my face, but I recognize the challenge. So I think a few brief words of acknowledgement are in order before we dive into the substance. So first and foremost, Sarah Chambliss, who's here in the room, is my doctoral student. Sarah did the lion's share of this work, and I think has done a very good job on this project, fantastic job, really. And so if you have any detailed technical questions, Sarah is a great resource, and I think we'd be delighted to answer any of your questions. I should acknowledge our two other collaborators. Julian Marshall is a close colleague of mine in civil engineering at the University of Washington. Many of you here in the room may know him. And then Chris Tessum is a research scientist at the University of Washington until the end of the year. He's just taken a faculty position at the University of Illinois, so he'll be moving back to the Midwest. I think it's also really, of course, we could not have done this project without our project managers here at ARB, and I really want to acknowledge both Zoe and Patrick for their fantastic support. And then I think it's, of course, incumbent on us to think about the 9 million Californians who live in EJ communities who breathe these disproportionately high levels of air pollution. And they're first and foremost in my mind when I did this work. And I think that the academic value of this work is important, but I'm hoping the practical importance of it will also be obvious to you. And so I'm looking forward to hearing what you think about what we've done. Before I go any further into the details of what we've done, I'd like to foreground maybe the key conclusions of the work so that you know what to take away from us over the course of the seminar. So there is a wide range in the exposure rate per unit of emission of air pollution in California. We call that relationship between what gets emitted and what gets exposed, that ratio, the intake fraction. We'll be talking quite a lot about that today. And the intake fraction of air pollutants emitted in California varies an awful lot spatially and by source category. In other words, some sources have a disproportionately high impact compared to others, and that's one of the really key things that comes out of this work. When we look by race, income, and especially by whether one is in a EJ community, as Zoe called it, or as is defined by SB 535, a disadvantaged community, DAC, I'll use that term over and over, we find significant exposure disparities in California. That finding, of course, is something that many of you are probably familiar with. Zoe just mentioned it. Our work perfectly supports that observation. And interestingly, there's not a single culprit. Almost all of the major source categories for PM2.5 in California contribute to these disparities. And so that means that there's probably not going to be silver bullets, although we do find some things that would be very efficacious to do. So as examples of things that have disproportionate impact on disadvantaged communities, the industrial sector, mobile sources, both on-road and off-road mobile sources, and then the natural gas and petroleum industry, especially refining and oil and gas extraction, are major disparate impacts. We designed this project not just to produce some results or journal articles, but actually to provide a tool to ARB and to the public at large, where there'll be an intake fraction database and a variety of other analytical tool databases that anybody can use to analyze and compare the efficacy and efficiency of different control measures at reducing total exposures and reducing exposure disparities in California. And we're holding a training this afternoon to show people how to use that tool, and we'll be happy to repeat that training in the future if anybody is interested in learning more. So Zoe teed up this talk very nicely already on some of the prior studies around the persistent disparities in PM2.5 exposure in California. I just wanted to highlight two studies here that really show that many specific source categories have disproportionate impacts on low-income communities, for instance, low-income non-whites, relative to the impact on higher-income whites in California. So there's a racial ethnic disparity in exposure in California. This disparity also is stratified by income, and we see clear inequality curves. This is on the bottom here from the work of Jason Su that shows that in almost all the major counties in California, you have an unequal distribution of exposure. So some groups of people are exposed at greater rates. And if we want to reduce these inequalities, well, I think generally what one would like to see is lower air pollution in California overall, and I think a lot of the policies that are already in place are well positioned to do that. In addition to reducing the total air pollution exposure burden in California, it would also be desirable to reduce these existing disparities so that we don't continue this trend of overall downward concentrations in California, but this persistent disparity remaining. This is some work from Julian Marshall's group from a few years ago, where they looked at, here, diesel engine emissions, but they looked at a variety of different source categories and identified zones within the South Coast Air Basin where emissions caused strong what they call an EJ disparity here as disproportionately impacting minority communities relative to the white communities. Those are the red zones. And then reverse EJ zones. So those are the green zones here where emissions disproportionately impacted whites relative to minorities. And so when you look at this picture, part of what you should be thinking about is where are the emissions? And part of what you should be thinking about is where are the different racial and ethnic groups? So our society is not uniformly distributed, but we're still rather segregated in places. And so partly what we're seeing on this map is the combined impact of where emissions are and how our society is segregated by race, ethnicity, and income, and so on. And so the thinking that came out of this work that Julian Marshall did was pointing towards this idea that maybe it would be helpful to develop decision support tools where we can identify locations where there are especially disparate impacts on minority communities. So as we think about what would be required to develop one of these decision support tools, it became clear to us that there are sort of two very important technical considerations to how one would develop such a model. On one hand, it's really important to have models that have adequate spatial resolution. So because many of these EJ effects come about because of the interaction of high proximity, so we're looking on the left here, the interaction of high proximity to emissions and high emissions, it's important to model these processes at fine spatial resolution. So I think Zoe's going to dim the lights here so that you guys can see the slide a little better. And I think I'd actually prefer that if people online can't see me, that's not a problem. They should be able to hear me and see the slides. That's really the most important thing. I understand you guys here in the room can't see. I think that's better, isn't it? Yeah. I would just turn it all the way off, Zoe, because many of the other slides are not going to work so well unless you dim it further. All right, so let me tell you about what this picture shows. What we did is I was part of this co-author team led by Julian Marshall at University of Washington. What we did is model environmental disparities using a coarse scale model and a fine scale model in the US. And so here we're looking at Chicago, and this is a coarse scale model where we ran the model at the coarsest possible resolution. This is a model where we ran it at the finest possible resolution. And so what you can see is that there are, of course, very fine scale gradients and concentrations when you run the model at fine scale resolution that basically get lumped into one big block when you model it at a coarse resolution. When you look at the racial and ethnic composition of here, Chicago, you basically find one grid cell that's mostly minority and then a bunch of other mostly white grid cells or more mixed grid cells when you have a very coarse model. And then you see that the segregation is actually much more fine scale when you start to zoom in at higher spatial resolution. What we found with this work is that if you use coarse scale models, you'll persistently underestimate the disparities compared to using fine scale models because so many of these disparate effects happen at fine spatial scales. So it became clear to us early on that we need a fine scale model in order to do this well. Those fine scale impacts are, of course, most important for primary particles. And I think that many of you in the room are probably aware of the distinction between what are called primary air pollutants and secondary air pollutants, but I'll give a brief explanation of this anyway. So a primary pollutant is a pollutant that is directly emitted, and what you experience in the atmosphere is the consequence of those direct emissions. A secondary pollutant is emitted, transformed, and then the exposure is the exposure to that secondary pollutant after some photochemical or physical or chemical transformation. And many of the pollutants we're exposed to that have important health effects are actually secondary pollutants, not primary pollutants. So most of the PM2.5 breathed in California and almost any place in the world is really secondary particles, not primary particles. And so if you want to control particle exposures, you need to be aware of the precursor emissions as well. Loud? Not loud enough. Okay, great. I'll speak louder still. So some of the major precursors of secondary particles include sulfur dioxide emissions, nitrogen oxide emissions, ammonia emissions, which largely come from agriculture and motor vehicles and a little bit from industry, and organics, so volatile organic compounds. All of those compounds are transformed into secondary particulate matter. If you don't look at secondary particulate matter in California, you're missing at least 60% of the exposure problem. And so we needed to build a model that could incorporate secondary particles as well. So let me tell you a bit about the goals of this project. We wanted to generate a comprehensive database of intake fraction and environmental justice metrics for the entire state of California at fine spatial resolution. So location-specific metrics so that we could compare against the exposure, the total intake and the environmental disparity impacts of emissions at different release locations, different places in the state at fine resolution, sector specific, so different emission sectors, looking at all these constituents of primary particles and secondary particles. So let me just break down the 4 acronyms there. Secondary organic aerosol, SOA. Those are secondary particles formed from the emission of volatile organic compounds. So VOCs are transformed into SOAs, SOA. Apologies for the alphabet soup here. Sulfur dioxide emissions are transformed into particulate sulfate, PSO4. NOx emissions are transformed into particulate nitrate, PNO3. And ammonia emissions are transformed into particulate ammonium, PNH4. So we needed to have a model that could incorporate all those, in addition to the primary particles that are about 40% of the problem. We developed a whole slew of metrics, more than 20, I believe, by race, ethnicity, by income quintile in California, by age, and by other socioeconomic groups, including the SB 535 disadvantaged communities, the so-called EJ communities in California that are now a major focus of policy efforts, as well as some things like linguistic isolation and other metrics of vulnerability. In addition to developing all these metrics, if you have a huge bucket of metrics, but you're not using it for anything, that's not so exciting. So we then applied this database as a screening tool. So we modeled exposure concentrations from 11 major emission sectors in California that basically are all the major emission sectors in California from human activity, and 59 subsectors within those 11 sectors that are more specific. So to give you an example, an emission sector might be on-road motor vehicle use, and subsectors might be light-duty gasoline or heavy-duty diesel vehicles, and so on. And then we wanted to identify the top sources contributing to exposure disparities in California. Our goal was then to provide these spatial databases as a tool so that other people could use them, and so this would be more useful than just what we could do alone. A couple of thoughts about this here. You may think this is a rather ambitious goal. This was a 18-month project, and so I think we achieved at a reasonable level of precision the goals we set out to accomplish, but there is still refining that can be done because this is designed to be a screening level tool. So when I present all the results I'm presenting to you today, I want you to have in the back of your mind, this is a preliminary screening level analysis. It's the best that you can do with a simplified reduced form tool, and it's the kind of thing you can use to identify hypotheses about what could be really effective. And then there's this iterative process where when these things emerge out of a screening level tool as things that might be of concern or strategies that might appear as particularly efficacious, then you can go back and apply more rigorous modeling approaches to identify whether you really believe what this tool puts out. So don't believe everything you think. A bit about methods here. So in order to relate emissions to exposures, you need a model, right? And there are a vast range of different modeling tools for air quality. You have very simple sort of single-level source models, like you could apply a box model or a Gaussian plume model, or very simple models. Those are too simple for doing what we need to do here because they don't capture the fine-scale spatial variability with enough fidelity. They are also not well suited to secondary pollution, which of course is so important. At the other extreme, we have highly resolved chemical transport models, things like CAMEX, CMAC, WRFChem. Many of you in the room are probably familiar with these modeling tools. They're very computationally expensive. They require an awful lot of training in order to be able to be used effectively. And while they produce really the state-of-the-science scientific results that, if done well, have very good fidelity to observations and everything else we know, they're way too computationally expensive to look at processes at very fine spatial scales for every emission sector in the state, looking at the disparate impacts community by community. That's not a task that those models today are well suited for, even though they get the science very well. And so we're using a model here that aims to sit in between those two extremes at the sweet spot that can tell us about fine-scale exposure disparities. So the model's called InMAP, the Intervention Model for Air Pollution. It was developed by Chris Tessum and Julian Marshall, our collaborators here. And one of the things that InMAP is designed to do is have high spatial resolution over populous areas. So what you should be seeing on the map here is an example of the InMAP grid for the San Francisco Bay Area, and of course this grid exists for the entire state. And what you're seeing here is that the grid is actually at very fine spatial resolution over populous areas. So the smallest pixels here are 1 kilometer. But then you notice that the grid gets much coarser, up to 12 kilometers in less populous areas of the state. And that coarser grid resolution, basically, the idea is, why spend computational effort on modeling at great precision concentrations in places where there's not that much population? So it's designed to focus the computational effort on where the people are. So it scales with population density. The model includes a treatment of secondary particles. And so primary PM and these four other constituents. The chemical mechanism is less complicated and sophisticated, and therefore less precise and accurate than a full-scale CTM, but we've robustly validated it, and it works reasonably well. The biggest uncertainties here are for ammonia emissions and the resulting ammonium concentrations. And so anything that relates to ammonia in this model, I would encourage you to view with a little bit more skepticism than anything else. I'm just going to preface that. But we still think that it's not crazy off. And one of the main ways that this model achieves such great spatial resolution at very moderate computational cost is it ignores all the fine time steps that is normally included in a chemical transport model. So it directly simulates annual average concentrations, as opposed to the way that a normal chemical transport model works, which is simulating hour by hour, or perhaps even at finer time scales, up to an entire year. And then you have these thousands of hours of simulations that make one annual average. Here, we have no seasonal resolution, but we can estimate the annual average directly. And we believe that's appropriate because many of these disparities are not about disparities in hour-by-hour air pollution, but really this persistent long-term disparity. When one thinks about health effects too, although we're not directly considering health here, many of the health consequences of air pollution are really long-term, not the short-term acute ones. And so we believe that that's a reasonable simplification. I've mentioned this term intake fraction now a few times, and some of you may be familiar with the cartoon I'm showing you here, with the idea being that this sort of points out the paradigm that we're thinking about this problem in. So on the very left, we have emissions, and of course emissions are the most common point of regulation for source controls. And ultimately, we care to reduce emissions because we want to reduce the health effects. But there's this long causal chain between emissions and the ultimate health effects. Emissions lead to ambient concentrations. People move through fields of concentrations that are spatially complex, leading to exposure. That's the contact of people with the concentrations, and then the inhalation intake of air pollution, intake. Those pollutants are then translocated into our body. They result in a variety of different doses at different parts of our body, and ultimately the health effects that manifest as the undesirable things we want to control when we control air pollution. Rather than just prioritizing things in terms of emissions, it can be helpful to prioritize sources based on their ability to create exposures or inhalation intakes. And so a metric has been developed in the exposure community over the past 15 years or so called the intake fraction metric. And as part of the training later today, I'll be giving an hour-long seminar on sort of the history of intake fraction and how it can be used. Intake fraction is a dimensionless term that rates a source on its ability to produce exposure. Specifically, it's the fraction of emissions that are ultimately inhaled by somebody somewhere. And so it allows you to convert from emissions into intakes. The value of intake fraction is that it allows you to identify sources that have especially high exposures per unit of emissions. And just as a very simple example of this, if you have a ship out in the middle of the Pacific Ocean, it may be spewing all sorts of pollutants, but if nobody's nearby, the health consequences, at least for any proximate community, are minimal. Now, if you have that same emission docked at the port of Long Beach, there's an exposed community nearby. So the release location really matters. The number of people exposed and their proximity to those pollutants. So those are two of the three Ps that we care about with intake fraction: population, proximity, and the third one is persistence. So pollutants that are highly reactive and remove quickly tend to have lower intake fractions than pollutants that are persistent, that they're long-lived, they're conserved. So in order to estimate intake fraction, you need a model. And the model is a model that links emissions to receptors. So this is called a source-receptor matrix. And the way that InMAP works is that you can run it in two modes. You can run InMAP to simulate a specific scenario, but you can also run InMAP to develop what's called a source-receptor matrix. So this is a matrix that links emissions in every grid cell of the model to the concentrations that result from those changes in emissions in any other cell in the model. So you can think of it as a gigantic matrix that relates emissions to concentrations, or conversely, concentrations back to the emissions that caused them. So we can go forward and backward, and that is one of the great flexible things about InMAP. So in the California grid, we have 21,180 grid cells. And when you think about the pairs of relationships, that's over 4.5 million pairs of sources and receptors. And because we care about local impacts, we're of course also computing the effect of emissions in one grid cell on the people who live in that grid cell itself, in addition to all the grid cells, upwind, downwind, et cetera, all around the state. So we're relating changes in emissions at a location to changes in concentrations at all other locations with the source-receptor matrix. And then we can compute the intake for emissions at any one location. We can generate what's called an intake fraction map. So you might have a source here. I'm going to point out it on the map here. So that's the source S. And then that source will cause effects on receptors all around the model domain. So in every grid cell, we're computing the effect of on concentrations and then the inhalation intake at every location throughout the state. So we're looking at the change in PM2.5 concentrations from a change in emissions at some location S to times when you multiply that times the population in every grid cell around the state, that population in the receptor grid cell R, times their breathing rate. So concentration is mass per volume. Our breathing rate is volume per time. The product of mass per volume times volume per time is mass per time. So that's the inhalation rate. So that's the intake rate, the grams or kilograms of air pollution being inhaled by a receptor population around the state. And one of the cool things about this metric is because we have demographic information about every grid cell in the state, we can sum up the exposures over the entire state or by specific communities. Maybe we're interested in low-income white communities in California. We could compute the inhalation intake fraction for that subpopulation, just as we could for high-income African Americans or any group that we might care about. So we're modeling affected receptors and tracing them back to the sources. Let me tell you a bit about these few metrics that we're working with. So the intake is the amount of air pollution inhaled by some specific population from a specific source. And so it is simply the sum of the attributable concentration experienced by a person times that person's breathing rate, summed up over the time you're looking at. Typically here we're looking at a year. And then we sum over all the individuals in the population's individual intakes to get the total intake of the population that we care about. The intake fraction then normalizes that by the amount of that pollutant that was emitted. So it's the fraction of the pollution that's emitted. And whereas intakes are measured in mass per time, so say 380 grams per day inhaled by some population, and that would be a reasonably large population actually, to give you a sense of the total inhalation intake of PM2.5 mass in California, we're looking at effectively thousands of kilograms of particles inhaled per year by all Californians. So it's actually not that much, but of course the concentrations of particles that we measure in California are in the, at most 10, 15, 20 micrograms per cubic meter of particles. So for micrograms, when you sum that over a year, you're talking about kilograms per year inhaled. Intake fractions are dimensionless, right? It's the fraction of emissions that are inhaled. But because it's inconvenient to say 0.00000015 or whatever, it's much more conventional to multiply these by a million and express them as a part per million. So 15 parts per million would mean that 15 grams per ton are inhaled. And this causes persistent confusion, I think, because we also measure pollutant concentrations as volume concentrations as parts per million. That's not what we're talking about here. We're talking about a fraction. Or when we look at particular emission sources and we care about their EJ impacts, we have two additional metrics that we talk about. One is the relative percent difference in the intake or the exposure concentration of one group compared to a different group divided by the average exposure for the, or intake for the population. So we're looking at that difference between one group and another. And those relative differences are often very useful when we look at particular sources. Some sources don't have especially large impact on air pollution overall, but they very disproportionately impact one group. And it's useful to be able to identify those large relative disparities because even if in absolute terms they're not enormous, they still have strongly disparate impacts. It's also helpful to have an absolute metric, the total difference in intake between one group and another. And so we can have that as a concentration difference. One group experiences a higher concentration than another, or an intake difference. We multiply by the breathing rate. much of what we're going to talk about today is going to be in terms of concentration differences between one group and another. So when we care about particular source categories, well, let me motivate this a little bit more first. It's often helpful to think about a specific source category and compare different source categories when we want to prioritize how to reduce environmental disparities. So if you were given a magic wand and said, your job is to reduce the exposure disparities in EJ communities in California, you might like to know which sources you should build policies around. I think that's a rather important question here in Sacramento and around the state, right? So in order to do that type of analysis, what we do is we know where the sources are in every grid cell around the state because we have emissions inventories, and then we multiply the emissions in a grid cell times the intake fraction for a particular group, and then we sum up over all grid cells, and then we have the intake from emissions from that source category. You can repeat for all source categories, and then you can make estimates of intake from emissions for all the major source categories and start to make comparisons. So we needed an emissions data set in order to be able to do this type of task. And I want to tell you a little bit about what emissions data set we selected because some thought went into it. InMAP was developed with the National Emissions Inventory. And so we're using the US EPA National Emissions Inventory for this project. When we set out to do the project, we actually hoped that we would, in addition, be able to use ARB's state-specific California emissions inventory, because for many reasons, it's the choice of policymaking here in California, but the data were not available in a format where we were going to be able to, on the timeline of an 18-month project, do this analysis using the state emissions inventory. But because intake fraction is dimensionless and it's independent of emissions, it would be reasonably straightforward to replace the emissions inventory that we've used, the US EPA National Emissions Inventory, with a state emissions inventory. So let me tell you about the emissions of some of the key pollutants in California. And I can acknowledge here that some of you online and in the room may know much more about this than I do. When we look at the total mass emissions of the different air pollutants, primary PM is actually one of the lowest mass emissions air pollutants in California, followed only by sulfur oxides. And yet, as we'll see in a moment, primary PM actually causes the most exposure. So in other words, thinking about this problem just in terms of mass emissions is not particularly sensible. NOx emissions are way higher than most of the other species emitted in California, but their ability to create exposures is actually reasonably low because the conversion from NOx to secondary particles is not so efficient, whereas primary particles are already particles. You can also see, just sort of skimming these different color schemes here, and the color schemes are going to be important for this presentation, that certain source categories dominate the emissions of certain pollutants. So for instance, for NOx, mobile sources and on-road and off-road mobile sources dominate NOx emissions in California. I think that should come as a surprise to no one. For VOCs, industry and the natural gas and petroleum refining sector, also very important. For ammonia, agriculture is extremely important, and to a lesser extent, mobile sources, and so on and so forth. Bit more about the model development here. The model is based on population data, of course. We're using data from the 2016 American Community Survey from the census. And so we are assigning at the 1 kilometer grid cell level the populations of different racial and ethnic groups. In California, the white non-Hispanic population is only slightly larger than the Hispanic population. And here I should speak a little bit about how the census defines race and ethnicity. There are races, for instance, white or Asian or black in the US Census, and then there is ethnicities, and the main ethnicity of concern here is Hispanic versus not. But the challenge is that if you basically have this matrix of race times ethnicity, it becomes too complicated to have a meaningful discussion in sort of the ordinary parlance of how we talk about race in society. And while I'm not an expert on this, the most useful way that we could simplify this was to treat white non-Hispanic and other non-Hispanic, the non-Hispanic population for every race as the races, and then for those that were Hispanic ethnicity, that became its own separate group. And so 37% of California's population is Hispanic, 40% is white non-Hispanic, 13% is Asian, 6% is Black, and 4% is multiracial and others. I think we could all have a conversation about the inadequacy of the census descriptions of race compared to and ethnicity compared to how we deal with this important topic in society, but we need a tractable and simple way, and so this is the way that we move forward. And I'm zooming in here on the South Coast region, so Los Angeles, San Diego, and so on, because it's the largest population center of California and also one of the most diverse places in California. And so you can see that the population settlement patterns are different. One other important thing to note here, of course, is that the intake fraction in California for whites and Hispanics is always going to be way bigger than for Black or Asian populations, simply because there are more people in those demographic categories. In addition, about a quarter of California's, well, precisely a quarter of California's census tracts and about 24% of California's population lives in communities, census tracts, designated as EJ communities or disadvantaged communities. These are places that experience a disproportionate pollution burden or environmental hazard, and they're vulnerable low income in some manner. So you can see the statewide map on the left here. What the statewide map does not render very well is the fact that a lot of these places are in the smaller, very concentrated urban domains. So Los Angeles or San Francisco, basically you can see these big gray patches. Those are the communities too. You just don't see them very well at the state level. When you zoom in on greater LA, you can see that a lot of the sort of central LA area is designated as a disadvantaged community, and many communities within the San Francisco Bay Area as well. And we're particularly interested in the disproportionate impact of pollution on those communities. So before I get to the results, I just need to apply a few more disclaimers about the limitations of these methodologies. So this really is a screening tool. It's not a substitute for more rigorous exposure modeling or more rigorous chemical transport modeling, but it's a great place to start for developing hypotheses. It's a reduced form model. The InMAP model has some inaccuracies associated with it. It performs moderately well when we evaluate it against much more complex models or monitoring data. But if you wanted to study a particular source and a particular subpopulation, there are better modeling tools for those very specific analyses. It only provides information on annual average concentrations. So if you care about extreme effects in a seasonal nature, so maybe you care about wood smoke effects in the wintertime, this is not going to be a great model for that. One key limitation is that the atmospheric chemistry in the model is based actually on an older version of the emissions inventory from the 2005 National Emissions Inventory. What this means is that we actually overstate the sensitivity of the model to ammonia emissions. So we think that we're probably overestimating to some level, the exposures caused by ammonia emissions in creating particulate nitrate and particulate ammonium, And so we are underemphasizing the ammonia part of the story in our results here. It is not that hard to rerun this model, the underlying model, using the updated atmospheric emissions inventories and to update the chemistry, and that's something that we're intending to do in the future in a future project. A couple of other thoughts about the limitations of the modeling. One is that this model is really designed to look at perturbations in concentrations. We have estimated here the total inhalation intake from the different emissions categories in the model, and I think you need to be a little bit more careful about thinking about totals and thinking about particular sectors, but it's a good way to look at the relative importance of different things, which is why we're doing it. We're, of course, based on residential census data, so people move around. We're not accounting for that. We're not accounting for the fact that people live indoors, and there are disproportionate differences in inhalation intake rate of air pollution because people live indoors, of course, and people with different income groups live in different kinds of housing stock. That's not included in the model. And then we assume that everybody breathes the same amount of air, which of course, and that's also not quite true. Let's move on to the findings. That's why you're all here. I've shown you this figure already. This is the emissions figure, right? So primary PM is relatively low in emissions compared to all of the sources. Let's now reweight this by population-weighted concentration. So we're going to apply the intake fraction, these other things, to get to the population-weighted concentration caused by each of these species in California. There we go. That's the population-weighted concentration. Emissions, concentrations again. So what you can see is that the greatest constituent of population-weighted concentration in California is actually the primary PM2.5. And ammonium is also high. We need to be careful about that for the reasons I've just said. And then the secondary organic aerosol from VOCs and the nitrate aerosol from NOx are the largest. Sulfate does not contribute much at all in California because there is very little coal left burned in California. That's the main reason. And Then we can also get a sense of the different sectors that contribute to these population-weighted concentrations. And one of the things you're going to see is that there are some things that are relatively large mass terms in the emissions inventory that don't have as large an impact on the population-weighted concentration. So if you study this figure for a second and move here, some things that are large in mass are far from people, and so they don't affect the population-weighted concentration so much. We'll see that much more in a moment. One cool thing about intake fraction is that emissions times intake fraction gives you inhalation intake. That's just by definition. And so what I've shown you on each of these three plots is the emissions on the y-axis. X-axis is emissions. Y-axis is the intake fraction for that pollutant. We're looking at PM2.5, VOCs, and NOx. And then the area under the curve, by definition, is the product of the x-axis and the y-axis. The area under the curve is intake. So what you can do here is, if you shade under the entire curve, you've got the total intake caused by those different pollutants. But if you look at the emissions with the highest intake fraction, those are going to be the emissions that have the disproportionate impact on intake. And so the top 10% of primary PM2.5 emissions, largely because they're close to receptor populations, result in 43% of the inhalation intake in California. So they have a very strong leverage on exposure. I'm also shaded on here the bottom 10% of the emissions for each of these categories. You can't see the shaded area, though, because it's so small. The bottom 10% of PM2.5 emissions and the bottom 10% of VOC and NOx and so on accounts for less than 1% of the inhalation intake in California. So these high intake fraction emissions often in very dense urban areas, have a really strong impact on the population-weighted concentrations and the exposure and so on. If you added this up over all the pollutants we looked at, the top 10% of emissions account for 48% of the inhalation intake. So there's some strong leverage there to go after these sources that emit in places with high intake fraction. When we look at the emissions, now I'm just going to zoom in on primary PM2.5, which is about 40% of the story. On the left here, I've plotted a bar chart of what are the sectors that contribute to the lowest 10% intake fraction emissions. So these are the ones that account for less than 1% of the inhalation intake in California. And on the right, I'm showing you the emission sectors that contribute to the 43% of primary PM2.5 emissions. So these up here in the top 10% that are very impactful on intake fraction. And you can see that I think there's two ways to look at this chart. One is that all the colors are represented in both of these charts. In other words, you're going to find some of everything in the bottom 10% and the top 10% in terms of their intake fraction leverage. But some things are strongly overrepresented in one sector versus another. So for example, fugitive dust emissions. They often take place in rural locations where the exposure impact is not so large per unit emission. The intake fraction is low. On-road mobile sources are more concentrated in dense urban areas where the intake fraction is high. And so on-road mobile sources and industrial emissions are some of the largest contributors to those top 10% emissions that have this really disproportionate effect on inhalation intake. So the location of the emissions really matters. And what I'm presenting to you here are some intake fraction maps. And Zoe, if you're able to dim the lights just for these next few slides, this would be really helpful to make people see it a little bit better. I'm sorry to make you run up there. So what we're seeing here is a map of the intake fraction on the left for primary PM2.5 and on the right for secondary nitrate. Note that the color scales are a factor of 40 different because the intake fraction for nitrate is so much lower than the intake fraction for primary PM2.5. But you can see similar spatial patterns. The spatial patterns are letting up hot where there are people who can be receptors to those pollutant emissions. And so we see strong effects of these pollutants in the South Coast Air Basin, in the San Francisco Bay Area, and then in the cities of the Central Valley, and a couple of other places in California each. One thing to remember here is that intake fraction is completely independent of emissions. So you can think of this as a map, not of pollution, but a map of the potential to create exposure if emissions were to take place in those locations, right? If we zoom in on the Bay Area, now we have intake fractions by race. So this allows us to think about where emissions are likely to strongly affect one race or ethnicity in the Bay Area. And so you can see, for instance, that the colors are the intensity of these color scales are different across these. So for instance, the African American population is smaller than some of the other populations in the Bay Area. And so the colors are less intense there overall because there are fewer people of that group to be exposed. And you can see hotspots also for where you have dense concentrations of people. So there's a hot spot in San Francisco because that's one of the most densely populated places in the Bay Area for intake fraction for whites. And then you can actually see sort of, if you look at the color scales carefully, communities that have a strong representation from one racial or ethnic group. This is the Bay Area. It's also even easier to see this in Los Angeles because the intake fractions are even higher. And so you can see where specific communities are located in proximity to potential emission sources. And again, remember that this is utterly independent of emissions. This is just saying, if you were to emit primary PM in one of these grid cells, what would the impact be on different racial or ethnic groups? Nitrate, the scale's a factor of 40 lower. And one of the things you'll see for nitrate is that the patterns are a little bit more spatially diffuse. And that's because you have atmospheric mixing over the timescale that it takes to convert NOx into nitrate aerosol. But although it's more spatially diffuse, it's not that much more diffuse. It's not like you have this big regional cloud. There are still reasonably localized impacts. And I was a little bit surprised by that, but we believe that to be true now. I've already pointed out to you that the intake is the product of emissions times intake fraction. I want to just highlight to you here a different way to look at these same data. So what we've done here is we've rank ordered each of these 11 sectors in California by their intake fraction, their sector average intake fraction. So for instance, cooking and on-road mobile sources have the highest sector average intake fractions. Now the width of each of these bars is the total amount of emissions. So you can see that there's a lot of industrial emissions or of primary PM2.5, and then also large emissions of on-road mobile sources and fugitive dust. But the intake fractions for each of those sectors are rather different, right? So the higher intake fraction sectors will have a disproportionate impact for a given level of emissions, and the area that you see plotted for each one of these is the total inhalation intake caused by each of these sectors. So you can, just by eye here, you can see that even though industrial emissions are about twice as large as the on-road mobile source emissions, the intake fraction is about half as big for industrial emissions compared to on-road mobile sources. And so the net impact of each of these sectors, despite having very different emissions, is about the same on inhalation intake. This is for primary PM2.5, and we've done this for all of the different species here. So what you should be seeing here now are these 5 different species. The big numbers on each of these plots are the total amount of inhalation intake caused by each of these species. So 597 kilograms per year from primary PM2.5, 527 from ammonium, 206 from SOA, 177 from nitrate, 24 for sulfate. Now, a high impact strategy might target sectors with both high emissions and high intake fractions. And the sectors that persistently have high intake fractions and high emissions are on-road mobile sources and industry in California. Those are the 2 big ones. So going back to the same figure, it's also helpful to blast this apart because there's different kinds of on-road mobile sources, there's different kind of industries and so on. So let's look at the subsectors, not just these big sectors. So I'm going to take this figure and now break it into subsectors. Now you're seeing the subsectors, and so you can see that the range of intake fractions is bigger for the subsectors than it is for the sectors. So you have, for instance, on-road mobile sources have higher intake fraction than the average mobile sources because they're in, some on-road mobile sources have higher intake fractions than others. And so I want to zoom in on a few of the big ones here. So on the very high end here, we have gasoline light-duty vehicles. They result in some of the largest intakes in California. And even though their emissions are just a hair less for primary PM2.5 than diesel heavy-duty vehicles, light-duty vehicles tend to be closer to people on average than heavy-duty vehicles because they're not operating so much on the interstate routes, or these sort of long corridors, say, between LA and San Francisco and so on. And so they have a higher intake fraction. Hence the bigger impact of gasoline light-duty vehicles compared to diesel heavy-duty vehicles. You have some sectors such as that don't have particularly big emissions, but they have relatively high intake fraction, so their impact is relatively big. Cooking is an example of that, 33 kilograms of intake from that. When you sum all of these highlighted ones, so just some of the big ones here, they account for about 75% of the total inhalation intake of primary PM2.5. So this is a sort of a quick tool for being able to apportion what the inhalation intake impacts are of different types of sources. And this is a useful place to start if you care about total exposure, but of course we also care about the disparities. So let's talk about these disparities now. So we've used this model to simulate, with a little bit of uncertainty, but I think we're still reasonably comfortable with this, the contribution to population-weighted exposures of different sectors for different emission sectors for all sorts of different racial and ethnic groups. So we're going to start with the all ethnic groups here, the average population weighted exposure is about 6.5 micrograms per cubic meter for the average Californian. Now that's lower than the total PM2.5 concentrations we know exist in California. And the reason is that our model is not including wildfire, it's not including some other biogenic sources, and it's not including emissions transported from overseas and from long ranges outside of our model domain. So we're missing some of the sources in California, but we have all the major anthropogenic emission sources in California. That vertical bar, you can see that this vertical bar here is the average, and so it's keyed off of the all category. Just off the top of the bat, some ethnic groups are way more exposed than others. So whites have among the lowest exposure concentrations in California. Hispanic and African American groups in California tend to have among the highest. And so there's several microgram per cubic meter difference in the concentrations of different racial and ethnic groups are exposed to in California. There are more modest differences by income quintile, but the lowest income quintile has a higher exposure than the highest income quintile. There are differences by income, but the differences by race are bigger. That's actually very consistent with the other environmental justice literature as well. And then let's go back to these disadvantaged communities here, these EJ communities in California. Now, because the EJ communities were selected, among other things, because they have high annual average PM2.5 concentrations, it shouldn't surprise you that the disadvantaged communities also are the most exposed subpopulation in California that we're looking at. And you can see that there's several micrograms per cubic meter difference between the average and the disadvantaged communities. And it's even bigger if you look at the disadvantaged versus non-disadvantaged communities. So they experience, compared to the statewide average, 45% higher PM2.5 concentrations in our model. Now, one of the things you'll see here is that all the major source categories contribute to the disparity. I hope you're picking that up from the picture here, but a few of them are indeed a bit more elevated. So just from this figure alone, you can start to see that on-road mobile sources and industry are especially large disparities for the disadvantaged communities. I'm going to show you a series of plots now that are going to allow you to verify for yourself the following hypothesis, that the differences by race are bigger than the differences by income when we think about exposure disparities. So what I've got here are A through K. These are the different emission sectors that we're looking at, A through K. And then we have the different income quintiles compared to the statewide average, which of course is going to be this horizontal bar. So what we're seeing here is that exposure to almost all the source categories in California, regardless of the income level, is higher for Hispanics than for the statewide average. So for almost all the sources we're looking at, for almost any income quintile, the Hispanic population is more exposed than the statewide average. And when we look at the income quintiles, we often see a sorting that the Q1, that's the lowest income quintile, is exposed a bit more than the highest income quintile. So that's true for agriculture, for instance. It's true for J on-road mobile sources. But there's some where it's reversed. So industrial sources, for some reason, it seems to be flipped around a little bit. And so when you look on a source-by-source basis, you're starting to get specific enough that maybe you don't necessarily see sort of this sort of classical sorting that the lowest income people within a community have higher exposures than the highest income. But the basic take-home should be pretty simple here, that on average, Hispanics, depending on the sector, are somewhere between 10 and 30% more exposed than the statewide average. And then the differences by income are usually much smaller than that. So now we can do this for all the different categories. Thank you, Zoe. So here is Hispanic as we were looking at before. Whites are less exposed than the statewide average in general. The Asian population is a bit more over the map. For some sectors, there's a reverse EJ, and for some sectors, there's a positive EJ difference. African Americans are very highly disproportionately exposed, and it does sort a bit by income. And then other race is a little bit, in general, a little bit less exposed than the statewide average. And that includes, among other things, the Native American population, which is a bit more rural, and so experiences cleaner air. So this allows us to sort of look at how different sectors are disproportionately exposed as a function of income. Let's leave income aside, because I think that it's actually much less useful than thinking about races or thinking about disadvantaged communities. What we're going to do now is take a quick deep dive into 4 sectors that the first 2 are really big for their overall disparity in disadvantaged communities. Each of these sectors alone contributes almost a microgram per cubic meter of disparity to the disadvantaged communities. On-road mobile sources is the biggest one. So its relative disparity is 53%, So relative to the statewide average, mobile sources lead to 53% higher concentrations in disadvantaged communities. That works out to a 0.9 microgram per cubic meter exposure disparity. And there are different subsectors, of course, that drive those disparities. Gasoline on-road emissions, because they tend to be closer to people than diesel on-road emissions, on average across the state, have about a 80% bigger impact. So 50.53 micrograms per cubic meter more exposure in a disadvantaged community compared to the statewide average for gasoline on-road emissions. 0.29 micrograms per cubic meter for diesel on-road vehicle emissions, and so on. Hopefully that gives you some sense of scale here. Industrial sources, 1 microgram per cubic meter higher in disadvantaged communities than in the statewide average, relative disparity of 59%. And a few of these have particularly high disparities. So material storage and transport, that includes, among other things, probably the fugitive dust coming off of material storage facilities in California, has a 111% disparity. So it's more than twice as high for the disadvantaged communities than for the statewide average. Industrial fuel combustion is another very important one. And then waste disposal and incineration is also a big source of exposure. Now we're going to look at two sectors that don't have a super high disparity in aggregate terms, in absolute terms, for the disadvantaged communities. So natural gas and petroleum sector has a 0.2 micrograms per cubic meter disparity, but its relative disparity is really quite high. So when we look at the disadvantaged communities here in this bottom bar, you can see that there's very large impacts from refinery and from the oil and gas production. And so, in particular, petroleum refining has a 102% disparity. So even though it produces about a 0.07 microgram per cubic meter, so in other words, a not immensely large in absolute term exposure disparity for the disadvantaged communities, it's twice as big in the disadvantaged communities compared to the statewide average. So that there's a very disparate impact. And if we go back to the real world and think about where we know refineries exist in California, that shouldn't be too surprising, the kind of disadvantaged neighborhoods that have large refineries in them. There are localized impacts there. Oil and gas production has a similarly large absolute impact, but the relative impact is a little bit less big. Off-road mobile sources, again, not as large in total disparity. Here, 0.3 micrograms per cubic meter for the EJ communities, but the relative disparity is pretty big. And in particular, there are two large subsectors within the off-road mobile source sector that have a really big EJ impact: aircraft and rail. Each of them are twice as big in the EJ communities than for the statewide average. So for rail operations, we think about where the rail yards are, the major rail corridors. There are localized impacts on EJ communities there. And then for aircraft, we're really talking here about the airport emissions. So the emissions of aircraft during takeoff and landing and all the airport support facilities. We're not talking about aircraft during the cruise phase of operation. And this largely comes from the airport emissions at LAX, because it's the biggest airport in the state, and it's in very close proximity to a lot of EJ communities. Okay, so I'm going to now introduce, I think, maybe one of the final types of charts that we're going to look at. We call these flagpole charts because they look a little bit like a flagpole. And what they're doing is allowing us to look at the particular subsectors that have an especially disparate impact on certain communities within California. So the way these charts work, let's start with the y-axis, actually. It's a little bit simpler. So the magnitude of the y-axis is going to be the same for all the charts. It shows how a particular emission sector contributes to the statewide population-weighted average concentration. So you're going to see some big chunks here that make sense. Gasoline passenger vehicles, diesel heavy duty, industrial fuel combustion. Those widths are going to be the same for those vertical widths are going to be the same for every single chart that I'm going to show you, because this is just the contribution to the statewide population average concentrations. But then the horizontal ordering and the rank ordering shows the disparate effect of those emission sectors, either positive or negative, on a particular community. So for instance, for the African American population, aviation has a strongly disparate effect on exposures for the African American community in a relative terms. So this is a relative scale. The difference in the population-weighted exposure concentration compared to the population-weighted average. So African Americans experience twice as high impact of aviation compared to the statewide average. And again, this has to do with where airports are relative to African American communities in California. Petroleum refining, again, has a highly disparate impact. So this is African American. Now that you've explored this a little bit, we can look at three racial and ethnic groups and the subsector impact on these 3 racial and ethnic groups. And I don't want to get into an immense amount of detail, but so we saw African American already. Railways have a strongly, in relative sense, a strongly disparate impact on the Hispanic population in California, as do material transportation and storage. Petroleum refining is also a big impact on the Hispanic population. And then there are some things that we haven't highlighted for each of these groups where there are sort of reverse EJ impacts. They're more strongly impacting other sectors, or sorry, other racial and ethnic groups than the racial and ethnic group that we're looking at here. So for every racial and ethnic group, there are some emission subsectors that actually reduce the disparities as opposed to increasing the disparities. All right, we are on to our final set of figures now. So I think what I've shown you so far should give you the impression that there are some sources of emissions that disproportionately affect the disadvantaged communities, and there are some sources of emissions that don't disproportionately affect the disadvantaged communities. They disproportionately affect the 75% of the state population that doesn't live in EJ communities, right? So what I've done here is I've rank ordered all of the emissions in California from the lowest to highest relative impact on the EJ communities. So the way you can read this left chart here is if we rank order all the emissions on the per unit emission, the change in concentration that's caused in the EJ community, a lot of the emissions actually decrease disparities in EJ communities. They more strongly affect the 75% of the state population that doesn't live in the EJ communities. And about a little bit more than half of the emissions increase disparities in EJ communities. And if you take the whole area under all these curves, the red wedge is bigger than the orange wedge. What that means is that there's a net disparate effect on the EJ communities. We're looking at primary PM2.5 here. There's about a 1.6 microgram per cubic meter exposure disparity for the EJ communities for primary PM2.5. So they breathe 1.6 micrograms per cubic meter more PM2.5 than the non-disadvantaged communities. So some emissions increase disparities, some emissions decrease disparities. And if one had the goal of decreasing disparities, you want to go after the emissions first that have a very strong impact on increasing disparity, right? So the area under the curve we might care about, that's the total disparity. So I'm going to plot the integral of this curve on the right side. So that's a fancy way of saying that we're going to start from the emissions that have the lowest effect on disparity. In fact, they reverse disparities. And as we add more and more emissions, we're adding all these emissions that decrease disparities. So if you just started with the lowest disparity half of the emissions, you'd actually, and you got rid of everything else, you'd flip the EJ problem the other way around. The exposures would be greater in the non-EJ communities than the EJ communities. That's not going to happen, but that's sort of the hypothetical scenario. If you keep going, you add more and more emissions that start to more and more disproportionately affect EJ communities, then that disparity starts to reduce. And then eventually the disparity goes to 0 because you have equal exposure in the EJ and non-EJ communities. And then you add the last 5% of the emissions, and that's what drives the biggest chunk of the disparities. So there are about 5% of the emissions in California that if they're fully mitigated for primary PM2.5, they would reduce the EJ community disparity down to 0. I think this is a really interesting and surprising finding, and it needs to be, of course, validated with more modeling. But it's saying that 5% of the primary PM2.5 emissions in California could be driving the vast majority of the disparity in the EJ communities. That if there's a good way to control those emissions, and there's more work to be done, obviously, in thinking about what those emissions are. If there's a good way to control those emissions, that's a really high leverage for reducing disparities. So tools like this and more sophisticated tools that could follow could be very, very useful in identifying these high impact strategies to reduce disparities. Interestingly, if we look at the types of emissions that make up that little wedge, that 5% of emissions here, that's on the right, and compare it to all the emissions, sources are the same sets of sources are represented in both cases. You have a little bit more industrial emissions, quite a bit more on-road mobile source emissions, but it's the same mixture of overall emissions. What this really speaks to is the fact that it's the location of the emissions, not just the type of sector of emissions that's really driving it. So it's reducing emissions in places that disproportionately affect EJ communities, and that in part is going to mean reducing emissions in EJ communities. I think it's fairly obvious, right? So I want to give you a sense of where this work might logically go next. We did this analysis on using the National Emissions Inventory. I think it would be helpful to apply this to the most up-to-date ARB emissions as well. And because we've done this using an intake fraction framework, it should be reasonably straightforward to swap out emissions for the ARB data set. It would also be sensible, though, to update the chemistry in the model to take advantage of the latest emissions inventories, and also to simulate future atmospheres where you might have a much more strong control of NOx and SOx and VOC emissions, because the chemistry will change as we move into future atmospheres. So having a future scenario, and that would be helpful. And then when we have these sort of sector-by-sector results, running those same sectors with a very detailed chemical transport model where we have greater scientific confidence in it, I think would be helpful for validating some of these most surprising findings. On the analysis side, we've done this as a statewide analysis, but of course our disproportionate impacts within certain air basins, and a lot of the policy is made on an air basin by air basin and community by community level, and so developing these versions of these metrics for specific regions and air basins I think would be logical. So much of the decarbonization and climate change policy that ARB is working on is going to have an impact on exposure disparity. And I think it's most people in California's hope now that the decarbonization efforts in California can be channeled in such a way as to reduce exposure disparities. And I believe that there's a variety of cool analysis projects that can be used to look at sort of the sweet spot between decarbonization and reducing EJ impacts. So we're very interested in conducting future analysis using these tools to identify different kinds of high impact strategies that could allow us to reduce disparities, reduce total exposure to all people in California, and also reduce CO2 emissions. Okay, I'm going to leave you with the key conclusions. I think you've heard many of these things already. So we've developed this screening method for linking emissions and disparities that can be useful for then exploring further hypotheses for different policies and different additional analyses. We saw substantial disparities by race and disparities by income too, but they're smaller than the racial disparities and ethnic disparities in California. Disadvantaged communities in California are experiencing about 45% greater than average exposure for the sectors that we're looking at compared to non-disadvantaged communities. And there really is no single culprit. Almost all the sectors contribute in some way to disparity, but there's especially high absolute disparity for the disadvantaged communities, for on-road mobile sources, and for industry. And high relative disparities as well for the oil and gas sector and for off-road mobile sources. Location, location, location. It's the location of these emission sources that really drives a lot of these disparities. And so releases in dense urban environments have high intake fraction, and they also have high disparate effect on disadvantaged communities and a lot of the racial and ethnic minorities in California that have been historically burdened. And so the high spatial resolution of this analysis can be really helpful for pinpointing the types of control strategies that might really help ameliorate some of these disparities. We've already made this tool publicly available within ARB, and we're going to make the whole tool publicly available once we publish our first manuscript about this. And we really invite all of you guys to use it. This is designed to be a tool that can help the entire community in California identify particularly effective strategies. And I think within reason, as a team, we're going to be very excited to help anybody who wants to use this. So please don't hesitate to reach out to me or any members of my group if you're interested in being able to use a tool like this. So with that, thanks a lot. Thanks for coming. And I'm happy to take questions.
Thank you very much, Dr. Apte, and this is great talk. And now we have the Q&A section. Any question from the room first? By the way, for those who join us online, you can send you a question to ciararm@calepa.ca.gov. It should be showing on your screen, so you can send your question to that email, and we will read it out.
Hi, thank you very much. This is Alvarado. It was a great talk. I really appreciate it. So my question is about the on-road mobile, and about kind of what goes into that. Is that the disparity because there are more cars or near disadvantaged communities, or is it more cars and dirtier cars? And then, lastly, is the brake and tire wear included?
Okay, so all this comes from the National Emissions Inventory, and I don't know deeply under the hood of how the mobile model and the other various spatial allocation models within the NEI allocate emissions within particular communities in California. My best understanding is that the age distribution of the fleet mix is not changing in response to social and demographic characteristics within neighborhoods. So in other words, this could be an underestimate if you had specific sort of zip code level data on the fleet mix operating different zip codes. You might see something where the disparity is even bigger than what we saw here. That's point number one. And so I think you're right to highlight sort of elliptically here the fact that the NEI is not providing the most detailed information on a neighborhood by neighborhood basis, and there may be better models out there for that. And then break and tire wear is included, yeah.
Hi, Josh. Jeff Austin.
Hi.
My question is about secondaries. So lately we've seen some interesting source apportionment analyses that show that, for example, SOA is increasing as a fraction of the PM2.5 pie, while things like sulfates and nitrates in particular that were a very large fraction in places like the Inland Empire and Southern San Joaquin Valley are now actually smaller than the SOA. And so I wondered, how do you feel about the relative performance of InMAP, which is the basis for this, on SOA versus some of the other secondaries?
So InMAP is InMAP traces its modeling back to the WRF-Chem model, and the WRF-Chem model does include a representation of a lot of the pathways for SOA formation. However, sort of the latest iterations of the volatility basis set and the most speciated emissions where we actually have a really good idea of where the primary organic aerosol is actually not primary organic aerosol, but is really sort of semi-volatile emissions and then the intermediate volatility stuff. That's not well characterized in either the NEI or InMAP. So if one wanted to take advantage of the best state of the science on SOA chemistry, this model is probably not the right place to start. And I think that limitation is a good one to be aware of as these models are further developed. Yeah.
So follow-up question. So is that because that part of the chemistry is just not very well understood and not very well modeled in models like WRF, or because InMAP hasn't caught up to WRF?
It's a little bit of each. So InMAP is not using the sort of latest and greatest chemistry that some modelers in WRF are using. And in addition, that would require a lot of work on properly speciating the volatility of the emissions in the NEI. And we're mostly just using the VOC emissions from NEI as opposed to the sort of, you're probably aware of the work that's been done over the past decade on that a lot of the primary PM2.5 emissions in inventories like NEI are actually semi-volatile and that they can lead to secondary chemistry. So that sort of advanced understanding is not incredibly well represented in this model, and that's something to be aware of.
Professor, I'm Roger Kwok from AQPSD. So this InMAP, is there a possibility of expanding its capability to a specific toxic species?
Particular toxics and species. So InMAP is designed principally for looking at PM2.5. And so there are not yet, at least, I mean, InMAP is still a model under development. So I think to some extent, anything is possible if people want to put the time into it. The models actually has a lot of this source code open sourced. Chris Tessum is the developer of it, and he's going to be continuing to develop that for a long time to come, is my understanding. I think that while there is interest in adding other species, one thing I'd point out to you is that for air toxics that are primary and reasonably conserved pollutants, you can use other model compounds. For instance, primary PM2.5 is not a terribly bad one here, as a reasonably good estimate of the intake fraction of those other species, because the intake fraction of any primary conserved pollutant is going to be about the same. And so to the extent that we think that many of these air toxics are effectively conserved over the timescales of local exposures that we care about, you may be able to use these for other air toxics. But I think an even bigger asterisk would apply for that kind of extrapolation. But it's maybe not a bad place to start to see if there's something there.
Okay, we can maybe start on a question online. So we received one question, and it says, interesting work. However, disadvantaged community selected based on population characters and pollution burden. Therefore, won't one expect a high correlation between emissions and disadvantaged communities? Perhaps analysis should only consider population characteristics.
Let me read the question as well, just so I have it with me here. This is a great question. The disadvantaged communities are, of course, selected as places that are disproportionately burdened. And so nobody should be surprised that we find that they're disproportionately burdened in our model too. I mean, I think we were absolutely expecting that as a result. We were also charged by the ARB for estimating, our task was given to estimate the particular disparate impacts in disadvantaged communities. And so I think the thing I'll point out here is that one can define any arbitrary community of interest with this type of modeling approach. It's not hard to select a different type of community. So if one would like to look at, say, a particular set of population characteristics as the receptor community, that's very easy to do with this type of model. But I think I'm taking the overall spirit of this question to be that if you put something in as the design characteristic in your analysis, you see it in the end, you shouldn't be surprised, and I completely agree. Yeah, Jeff.
So I was involved in creating some of the data layers for Kellen virus screen, and one should bear in mind that some of the exposure metrics or pollution metrics, as opposed to demographic metrics, are based on things like hazard proximity, for example, or they're based on other pollutants besides PM2.5. So there's a whole lot in there besides PM2.5 concentrations or PM2.5 emission sources. So yes, that absolutely we would expect the top quartile of Kellen virus screen communities to have to be disproportionately affected, but it's not as clear cut as one might think.
Okay, yeah, that's helpful. Alvaro had a question, I think, too.
Following up on the SOA question.
Yeah.
So I can see how your conclusions are true for primary PM2.5. So what about controlling NOx and VOCs? Since those impacts are going to be more downwind, will they have the same kind of disparate impact? Yeah.
Yeah, let's go back to the intake fraction maps, because I think they speak to that very nicely. It's quite a ways back here. So this is primary PM2.5 here. And you can see that there are these localized hotspots of high intake fraction in places where there are large receptor populations, right? That's primary PM2.5. Here's nitrate from NOx emissions. Primary PM2.5, nitrate. It's only a little bit smeared out. So the chemistry is not so slow that you don't get these sort of localized impacts still. And we're reasonably confident in that chemistry. The other thing I would point out, that this is sort of well beyond what InMAP can do, but it's on the SOA question, is that there's more and more sort of cutting edge work coming out of the SOA measurement campaigns that I've been tangentially involved with that are showing that SOA can form over much more rapid timescales in urban environments than we previously thought. So that you actually can see, like we made, in conjunction with Carnegie Mellon, we made mobile measurements of organic aerosol composition in Oakland. And one of the things we were surprised to see is that in downtown Oakland, we see higher SOA than in other regions of Oakland. And that's probably because there are semi-volatile precursor emissions that are happening, SOA precursor emissions that are happening in these densely populated regions that don't take much atmospheric aging at all to get SOA, and so you get in this localized SOA formation. You guys are maybe aware of Brian McDonald's work on volatile consumer products. That's, I think, really affecting the summary of that work is that it turns out that in places like Los Angeles, consumer products like deodorants and paints and all sorts of things that we're using in like household cleaners are actually bigger sources of reactive organic compounds, reactive VOCs that can be really rapidly oxidized to produce SOA than are, say, traffic emissions now. So there are these compounds that are really highly reactive that we have in our consumer products. And I think somebody described it as a chirping volcano that we have over many of our cities. So these are compounds that can be really rapidly oxidized. And I think there's more and more sort of work happening in the atmospheric chemistry community now that suggests that you can get these reasonably fast processes producing SOA even within urban environments. So there are intra-urban gradients in SOA as well. They're not nearly as big as the intra-urban gradients in primary particles, but because SOA is such an important contributor, they may account for some part of the disparity. That's still pretty far. It's pretty bleeding edge research, but I think eventually you might see that built into models if we get more confidence about it.
Okay, since we talked about consumer product, there's another question from online. It's from Peggy Jenkins of ARB.
Yes.
So she's asking, have you done any work looking at or including indoor sources emissions, for example, like from cooking, which has been shown to be a major source of PM exposure in several studies. This would seem to be especially important in examining various ethnic group differences. If you have not done this yet, could you model or calculation be used to include this?
This is a great question from Peggy. And of course, indoor sources and indoor exposures are a very important part of the overall inhalation intake that we're exposed to. This contract was specifically focused on outdoor emissions, and so we didn't do that. But the intake fraction framework is flexible enough that in principle, one could develop an inventory of indoor emissions as a function of income and socioeconomic group if one wanted to collect those types of data on indoor emissions, and then build models of housing stock that could look at, on one hand, the infiltration of outdoor pollution, and on the other hand, the ventilation away of indoor pollution. And I think this is a modelable problem, but the question that Peggy's asking here looks to me to be at least as big as Sarah's PhD. So another PhD student can tackle this topic in the future.
You. Another question from Thai-Phone of OIHA. So thank you for the wonderful talk on intake fraction. I wonder how the models can be validated, even partially, to see how well the predictions fit in reality. Thanks.
Yeah, that's a great question. And this goes back to my point earlier that you shouldn't believe everything you think. And I think that there are a couple useful ways to validate these models. One is that it's, of course, possible to run, there are other models out there that simulate emissions to concentration relationships. The emissions to concentration relationship is really what governs the intake fraction. And the emissions to concentration relationship is really the core thing we care about here. It's how different emission sources disproportionately affect different groups. And there are different ways to look at this. One is that you can look at tracer methods. This is something that's expensive to do, but it is possible that you can look at tracers of particular emission source categories and understand, based on detailed measurements, what the concentration distribution looks like. That's not practical at large scale, but I think there's the scope for some experiments around that in California. And I think the much more feasible thing to do, of course, is to use very highly validated chemical transport models that are routinely used by policymakers here at ARB to run certain scenarios that can answer the same kind of questions that these scenarios that we're looking at here could speak to. And then we should see whether we're getting approximately similar results. And if there are large deviations, then I think that would suggest that this model would need some tune-up. But the bottom line here is that this should be a useful screening tool for identifying some interesting hypotheses. And when we start to see smoke in particular, when there's smoke, we want to go look for the fire, that this model is the smoke, and then we need the fire with these more sophisticated tools.
Thank you. Another question from Mohammed Abdullah of ARB, and he's asking, I have a question regarding biogenic emissions. As modelers, we know that biogenic emissions can greatly influence the formation of SOA depending on the location in the modeling domain. So what do you think, how your analysis would have changed if you were to include biogenic emission in work?
Yeah, so I should actually, that's a great point, so this question about biogenic emissions. We're not directly simulating the impact of biogenic emissions, but actually if you look at the underlying models on which InMAP was developed, the biogenic emissions were included. Really what InMAP is doing is telling you a delta in concentration for a delta in emissions. And so the idea is that that sensitivity to emissions that creates concentrations depends, among other things, on the biogenic emissions that are in the baseline WRF-Chem runs that are setting up InMAP. But for the purposes of looking at the intake from modifiable factors within California, biogenic emissions, at least to first order, are not things that we're contemplating modifying, although they may change over time anyway. And so we're not looking at the impacts of biogenic emissions here because they weren't part of our charge. But they're not completely outside of the framework of the modeling. They go into the WRF-Chem runs that develop InMAP.
Thanks. Another question from online. So it's from Bart Course, and he says, Josh, excellent work and well presented. What is the vertical resolution of the model, especially in regards to fully distinguishing the difference between emissions in breathing zone, for example, like tailpipes, versus elevated sources? And I missed how you addressed year-to-year differences in meteorology. Would you expect much difference if a broader range of years were included? I was surprised that secondary nitrate was a factor of 40 lower in its relative impact compared to primary emissions. Were offshore NOx and SOx emission from ships included in the modeling? These are expected to fully convert to nitrate and sulfate by the time the emissions reach shore and impact a broad, densely populated area in Los Angeles. A long question. Yeah.
Yes. Thanks, Bart, for all the questions. So let's talk about vertical resolution first. We simulated 3 emissions stack heights: ground level, mid-height, sort of high stack emissions, and we apportioned the emissions to these various stack heights, and did include plume rise in some of the calculations as well. Emissions directly into the breathing zone, of course, in the model. In the real world, you can be driving in a car with your windows rolled down and passing another tailpipe, then you're getting emissions dosed straight into your vehicle cabin, or emissions straight in your face, or whatever. That of course is all lost when we have even a 1 kilometer by 1 kilometer grid cell pixel. So there are these elevated hyperlocal exposure enhancements that we know to exist in the real world, and those are not well characterized by this model. But yes, we are accounting for the differences in release heights of different emissions. In terms of year-to-year differences in meteorology, we didn't look at it. It clearly is important in California because we do see year-to-year differences, rainy years, windy years versus dry, stagnant years in both meteorology and in air quality because of other sources. And that is important, but I'm not sure it dramatically is going to affect the relative ranking of things, and the relative ranking of things, I think, is one of the key take-homes from this. And then finally, to your point about secondary nitrate, Bart, I pulled up the slide here that shows the aggregate impact. So the intake fraction of particulate nitrate from NOx is way lower than primary PM2.5 because the conversion efficiency is not super strong. But NOx emissions are also way, way higher, right? And especially in many of the urban zones where we care about exposures. And so there's less than a factor of 3 difference in secondary nitrate concentrations versus primary PM2.5 concentrations. So the factor of 40 is just the intake fraction, but you do get strong exposure from nitrates still.
Okay, we have no more question from online. Any question?
Well, okay, one more from Alvaro, it looks like.
We have one more question from the room.
Thanks. Sorry, asking a lot of questions.
I really appreciate it.
So it seems like the method really accounts for which emissions affect the most people, right? So
Yeah.
is there a way to run this in a way that accounts for which emissions have the highest concentrations on people? So it's like, which emissions account for the greatest risk, even for small populations? So
Even for small populations.
yeah. So I mean, if we skew this towards urban populations, we leave out the vast land area of California,
Of course,
and certainly like the Central Valley and other parts of the state.
Yeah. So when I sketched out the future work that I'd like to see happen in this kind of agenda, I think separating by air basin is a really good way to do that. But we could also separate by urban versus rural classification. And the framework is flexible enough that you really can select any set of receptor grid cells you care about. And most of the receptor grid cells, of course, as you say, are rural. And there's absolutely no reason why we couldn't do that. It's just, we had to stop somewhere. And I think that's a very sensible point because the mandate of air quality policy should be to improve air for all Californians. And of course, one does want these really high impact wins, but there needs to be something on the table for everybody. And I would completely agree with that sentiment.
Great. We have no more questions. So with that, please join me to thank Dr. Josh Apte for this excellent work and the great talk. And for those who want to see the final report, we're going to upload it to our website. And please come back to the research seminar webpage. We will add a link to the final report. You will see the detailed results. And if you have any questions, you can either contact Josh or myself. And thanks again for joining us for this seminar. And you have a great day.
And happy Thanksgiving.
Yeah, happy Thanksgiving.
Thank you.